All right, so in this video, we're going to talk about the end behavior of rational functions. So last time we talked about polynomial functions. What a rational function is, it's it's what you get when you take two polynomials and are dividing them. That's considered a rational function. Anytime where anytime you have variables in the numerator and the denominator. Well, mostly the denominator. Yeah, the denominator is where it's important. So you should have this set of notes in there somewhere. Read those. It kind of defines the rules, but I'm going to go show you the rules. Okay. So the first case is considered the bottom heavy case. And the reason this is bottom heavy is because the degree of the denominator is degree 4. Okay. It's not because it has two terms. It's just because the degree of this polynomial is higher than the degree of the top polynomial. Right? It only has degree 2. So uh, I want to know what happens to the value of this function as x gets big. So let's pose it this way: as x tends towards positive infinity, as x gets really large, what is happening to the value of the function, to the y value, the f of x? So to figure this out, I just want to play around with it. I'm going to plug in a big number for x. I'm going with 50. If I plug that value in, I'm going to get 3x squared, x to the fourth, minus 1, okay, and I get 0.001 in a bunch of little decimal places. This is a really small number, right? All right, if I went with a bigger value, say like 75 for x. Okay, try it again. Yeah, I start getting into this scientific notation form where it's, you move the decimal to the left 4 places. This represents a very small number, by the way. In fact, the bigger number that I plug in for x, the smaller and smaller my answer is going to be. Okay, uh, the the general way this is going to play out, when you have a rational function where the degree of the bottom is bigger than the degree of the top, as these x values get really big, the value of the function is going to go to 0. You always get the same answer in this case. All right. And that's because you're taking like a big number, but you're dividing it by an even larger number. Remember, for large values of x, a degree 4 is going to outpace a degree 2. This is what the graph of that thing looks like. Okay. So you see here, as I go out to the right forever, if I zoom out a little bit, as these x values are increasing, see here they're at 15, 16, 17, my y values are getting closer and closer to 0. And that's true whether I go to the left or to the right. Now, I know there's a lot of other stuff happening here, but we'll have to save that for another day. Right now, we're just talking about end behavior. All right, that's case 1, bottom heavy. Case 2 is what happens when the degrees are equal. Okay, uh, the top and bottom are both degree 3 polynomials. All right, I know this one has more terms, but that doesn't matter. It's really just this first leading term here. That's the only part that really matters when you're trying to find the end behavior. So let's go ahead. We'll plug in. We got 75 stored, right? Yeah, we'll use 75 again. Let's figure out what happens to this function for large values of x. 6x to the third minus 4x plus 1. 2x to the third minus x squared. Okay. All right, we're getting 3.0197. So we're not going to infinity. We're not going to 0. Let's do a larger value, say 1,000 stored at x. If I run this again, I'm still around the 3 mark. All right. So it looks like as x approaches infinity, the value of the function is equaling or is approaching 3. That's what's going on here. All right, where this 3 comes from is the 6 divided by 2. Okay, 6 divided by 2 is the number that gives you 3. So if you want to find the end behavior for a rational function whenever the degrees are the same, what you do is you take those leading coefficients and you divide them. That's how you get this end behavior number. If I look at the graph of it, there you go. All right. As you go out to the right forever, it's getting closer and closer to 3. And as you go out to the left forever, the exact same thing's happening. It's starting to level off at 3, or approach a y value of 3. Okay. So those are your first two cases. And then the third case. This one is a little bit trickier. This is the top-heavy case. There's several different things that can happen here. All right, what you do for the top-heavy case. So I know it's top-heavy because it's a degree 5 versus a degree 3. What you're going to do in these cases is ignore the other terms, okay? As the x values get super, super large, these terms right here don't really matter so much. The only thing you need to focus on is the negative 24x to the 5th over 12x to the 3rd. You could say that as x gets big, this function kind of approximately equals this right here. Now, what you want to do is you want to simplify this expression and then use those end behavior rules from our polynomial side to answer what the end behavior is. Okay. So if we simplify this, the negative 24 over 12 will give us negative 2. And then x to the 5th divided by x to the 3rd will just simplify down to x squared. You subtract the exponents. And this right here becomes our defining factor, our defining characteristic. All right, so because this is an even function and it has a negative leading coefficient, I know that this one's going to be one of those down and down functions. So as x approaches, we didn't really ask the question, but as x approaches positive infinity, the value of the function is going to approach negative infinity in this case. Okay. I won't bother, but if you plug in a very large number for x, you'll see that this one actually blows up negative. It's going to get bigger and bigger negative. Let me go ahead and we'll do the one other example from our paper here, our notes. Okay. So as x approaches infinity, what will the value of this rational function be? Okay. So for large values of x, again, you can kind of ignore these pieces right here and just focus in on 4x to the 6th over x to the 3rd. Okay. Now what this is going to become is 4x to the 3rd, because 4 divided by 1 is 4, and then you cancel the 3 x's from below with 3 of them up top. And if you remember on our polynomial side, this is going to be one of those, well, what is it? It's got an odd degree power, and the leading coefficient is positive. So this means it's going to be one of those down to up functions. And as x approaches positive infinity, okay, as you go to the right forever on one of these graphs, the value of the function is going to approach positive infinity as well. Okay. So that pretty much summarizes The end behavior for rational functions. Yep, that's all of them.